A thiol, where?
SHNS.
Mm-hmm. Okay. Yep, so that's thiol. Anytime you see a sulfur, that's a thiol. So you see that one. What else?
The one to the left, all the way to the front with the double bond to the O.
That's a,
That aldehyde?
that's an aldehyde. Mm-hmm. So it's always on the end. It's when you have a carbon double bonded to an oxygen with a hydrogen on the end. That's an aldehyde.
Phenol.
Where?
The OH.
Mm-hmm. So the aromatic with the alcohol group, that is a phenol.
Amide below it.
Yep, just below it. This is an amide. Okay, so that's an amide because instead of a ketone, because see the nitrogen connected. Okay, so that's the kicker between them.
The ether at the bottom and the middle of the two.
Okay, yep, this is an ether.
And then they're both on either side of the aromatic.
And then these are both aromatics. One here, one here. Oh, there's another one. Yeah, I knew there's two aromatics. I just counted one aromatic. Yeah, it's an amine. Mm-hmm. So this one. So when you look at that nitrogen, the carbon next to it doesn't have a double bonded oxygen. See the nitrogen? So this is an amine. Good. So you'll have that card, okay? So, and I posted this on Moodle too, so that if you wanted to use this to look at, I just found like, it's probably not the best card that I ever could have done because some students look at this and are like, this confuses me even more so. So look back on that chart that we made, look back on the examples that we've gone through so that as you're looking, you're a little more familiar. You really just have to try to pick them out. So coming down, this, come on, not that far. It's like, nope, not going. So coming down here, oh, that's neat. Thanks. Look at this one. I don't even know. I don't even know right now. Just go away then. I'll put them back in later. So coming down, looking at these two, and it's this group together. Let me see if I can not. Okay. I don't know how that happened. Looking at those two, tell me, one, are they isomers? Yes or no? And how do you know?
There's 6 carbons.
Okay. 1, 2, 3, 4, 5, 6 carbons. There's 7 carbons. You got to count the total number. 7 carbons. Okay. 15 hydrogens. So C7H15 and the chlorine. Okay. So down here, 1, 2, 3, 4, 5, 6, 7 carbons. 15 hydrogens and 1 chlorine. So are they isomers? Yes. They have the same formula. Okay. So if they have the same total number of atoms, then they're isomers. So then the next question is, are they conformational isomers or are they structural isomers? And how do you tell? Okay. And the easiest way to do that is to just figure out the name. Okay. So what's the name of the top one? It's not 7 carbons in the longest chain, 6. So it is a hexane. The group at the top, this is a methyl. This is a chloro. Which way are you going to number?
On the right.
1, 2, 3, 4, 5, 6. So the methyl is a 3, chloro is a 1. Okay, so what's the other one? Longest carbon chain is?
6.
Oh, 6. So it is a hexane. Groups hanging off?
The same thing.
This is a methyl, and this is a. So do look carefully. Don't mistake a carbon for a chlorine or vice versa. So do make sure you check them. And then what do we have to do? Okay, which way you want to number from? Okay. 1, 2, 3, 4, 5, 6. So the chloro is a 1, and the methyl is a 4. So this is a 1-chloro-4-methyl hexane. The other one's a 1-chloro-3-methyl hexane. Are they the same molecule? No. The methyl's on a different carbon. So that makes them structural isomers. If they had the same name, then they would be conformational. They'd be the same molecule, just drawn differently. Conformational isomers are the same molecule, just drawn differently. Structural isomers are different molecules because they're put together different. The bonding arrangements are a little different. Okay, so last one. How many chiral carbons in this molecule? See if it'll let me go down without acting crazy. So how many carbons total? 5. Okay, so there's 5 carbons. You could have 5 chiral carbons. The rule is 1, the carbon has to have 4 single bonds. Are there any that have double bonds or more than single bonds? No, so that's a check. All of them have that. But 2, all the groups attached to the carbon must be different. So looking at the first one, carbon, this carbon, is it chiral or no? Why?
There's 2.
It's got 2 hydrogens, okay? Can't have more than 1 hydrogen connected to it, so this one's a no. So what about this one? No, because, again, 2 hydrogens. So the groups on the right and the left are different, but the above and below are the same. So that's a no. So now, this one. Group above is a bromine. Group below is a hydrogen. Group to the left is this entire group. Not just the carbon next to it, but the entire piece on that side. And so that side, there's an oxygen, and then the entire piece on this side has 2 chlorines. So those are different? Yes. Okay? So this one would be a chiral carbon. So the entire group to the left and the right are different from each other, different from the ones above and below. What about the next one?
Yes.
Why?
Because both sides are different.
Okay, so if we look at this one, hydrogen above, chlorine below, single carbon and a chlorine to the right, and then to the left are 3 carbons. So when you're looking at them, you're thinking about it from the entire thing. So this entire piece, and then this, and then this. So that's what you're really comparing when you're thinking about a chiral carbon. So all of the part to the left and all of the part to the right count. Okay, so yes, this is a chiral carbon. What about the last one? Why? Yeah, it's 2 hydrogens. That's really the easiest one to do. It's just look to see if there's more than 1 hydrogen, so you don't have to worry about anything else. If you only see 1 hydrogen, then you start looking more closely. Okay, well, what are the other 3? Are any of them identical? So if you had like 2 methyl groups, that wouldn't be chiral, because a CH3 on one side, CH3 on the other side, that would not be chiral, because it's got to be different groups, not just different than hydrogen, but they have to be completely different themselves. Okay? So hopefully that'll help, that like little review. It's not really a little review. So you should hope, if you go through this and you're like, wait, I don't remember this, then this is like, it's all in order. So it is the order that we actually covered material. So you should be able to go through your notes and check them off and be able to practice examples that we've covered as we go through. So for example, Just keep throwing in the examples. So for example, backing way up, this is backing up into chapter 3. Okay, so looking at this one, CFH3, already have it written out. What is its VSEPR?
A,
Mm-hmm.
B, three.
Remember, the central atom is carbon.
Yeah.
How many groups does it have connected to it? 4.
And
Okay.
then N.
Is there any N's?
No.
Is there
Oh,
N? Yes,
you would
because,
count the F.
right, it's
Okay.
just, it would only be the non-bonding electrons around the atom you're talking about, okay? So carbon, when it has 4 single bonds, always is what shape? The tetrahedral. Remember, pyramidal is what you see when you have one pair of non-bonding electrons like nitrogen does. Okay, AB4, tetrahedral always. If you see a carbon with 4 single bonds, it's always going to be tetrahedral. Okay, it doesn't matter what it's connected to, it's always going to be tetrahedral. So with this, polar or non-polar?
Non-polar. Or polar because it had, I don't know.
Remember,
Oh, that was polar.
what was the rule in looking?
If it can't be changed.
Remember, what are the 4? What are the 4 that you look for? We're trying to figure out. They're which ones?
Oxygen, nitrogen.
Nitrogen, oxygen, fluorine, and what's underneath fluorine? Chlorine. So if you see one of those, if you only see one, it's polar. Okay? Otherwise, if you have more than one, then you have to look at how it's arranged. Are they evenly arranged like carbon dioxide, or are they all on one side?
Like a linear structure.
So in this one, because it's tetrahedral, fluorine is the most electronegative element that exists. So that means all these electrons are going to get pulled to that side. So the carbon doesn't hang on to that shared pair very much. Its shared pair are way over near the fluorine. So this bond is way up over here. And so this side becomes more negative. This side becomes more positive. That creates a polar molecule. Whereas if I had methane, CH4, same shape, same tetrahedral, but there's no nitrogen, oxygen, fluorine, or chlorine, so these bonds are shared very evenly. So there is no slight negative insidedness to it. This is a nonpolar molecule. So if you see one nitrogen, oxygen, fluorine, or chlorine in a covalent molecule, then you know that the sharing of electrons is not even, and it's going to create a polar molecule. If you see a covalent molecule that has 2 electronegative atoms, like carbon dioxide, so remember, here's your oxygen, so you automatically go, well, that means that the oxygens are going to pull the electrons this way and this way, but they balance each other because they're on opposite sides, so they will balance each other, even though they're electronegative, creating a nonpolar molecule. So no electronegative atoms or even numbers of electronegative atoms, like balanced arrangement in the molecule, that'll create a very even sharing of electron pairs and creates a nonpolar molecule. So what about that one? What about CH2O? What's the VSEPR? It's AB3. Is there an N? Does carbon ever have an N? No, carbon never has non-bonding electrons. So notice there's no dots. There's no dots around the carbon. I don't care about the dots around the oxygen. It's the ones around the central atom. So that's AB3. And if it's AB3, what's its shape? Nope. Bent as water. It does begin with a P. It's trigonal planar. Yeah, that's why I went through this. These get 120 degrees from each other. 120, 120, 120, because that makes 360 a full circle. And so it looks like a little triangle, and it lays flat. So that's why they call it planar. So the carbons here, oxygen and hydrogens are all sticking off like a little triangle from them. What about polarity? It's polar. Because the oxygen's going to pull the electrons towards it, creating a more negative side around that around the oxygen. So the side where the hydrogens are is going to become more positive. Slight positive here, slight negative there. Okay, so last big challenge, then we're going to move on. 7.83 times 10 to the 22nd molecules of carbon dioxide is how many moles?
Well, carbon is 12, right?
But if we have molecules and moles, what do you need to use?
That's how much it is.
That's grams and moles.
Oh, we gotta use the, what's it called, that guy, avocado.
Yeah, avocados number. So 6.02 times 10 to the 23rd molecules is 1 mole. So if you see molecules and moles, it's just a single step. It's just a single step, but you're going to use this. So 7.83 times 10 to the 22nd molecules times in a line. What unit do you put on the bottom? Molecules on the bottom. The unit you're given goes on the bottom. Moles goes on top. Just a single step. The biggest challenge is making sure you put it in your calculator right. I don't think I have a calculator. Don't forget your calculator. Like me. So put it in. So that would be 22nd. What'd you get? So in this one thing to, if you're using your graphing calculator, use your parentheses. Okay, so put parentheses 7.83 times 10 to the 22nd, parentheses divided by parentheses 6.02 times 10 to the 23rd, parentheses, so that it'll group them. Because otherwise it'll like divide the times 10 to the 22 by 6.02 and not the rest of it. So it won't necessarily do it all together. What'd you get?
What's that? 1.3.
So you got 1.3. Did you get a times 10 to the, or?
Times 10 to the 45.
Oh, no.
845.
No, that can't be it. That's why I said put it back in, but put it in and use those brackets. Did you get one yet? So put it in and put this around it when you do the division. 0.1300664452. So 7.83 is 3 significant figures, so I would just use 0.130. Practice that. Make sure you can do that. Make sure you can get it. Okay, put yourself a note about that, how it goes in your calculator, because you may set it up right, but then you just put it in your calculator wrong, and then you get the wrong answer.
Can we get a bigger
Okay.
note card?
Huh? We need a note card. It's like 3 pages long. We need a 3-page note card. but practice them, okay? When you're putting in two numbers with exponents, that can be the challenge. So if I have 0.130 moles of carbon dioxide, how many grams is that? So there's the second one. Now that, when you see moles and grams, then you want to know the mass of carbon dioxide. So carbon weighs 12. Oxygens weigh, and I got two of them. So that's 12 and 32, so that is 44. So I have 44 grams in 1 mole, so 0.130 moles times, what unit goes on the bottom? Moles. Unit you're given goes on the bottom. I said 44 grams in 1 mole. Moles and moles will cancel. So 0.13 times 44. 5.72 grams. And that you don't have to round because it's 3 significant figures, and that's like what the number actually comes out as. So really the big number in molecules is just making sure you put it in your calculator correctly. All right, so chapter 5 is all about chemical reactions. There's really no math in this, it's all theory. There's really just theory, chapters 5 and 6. They're all just theory. So the study of this energy, like what is energy and how is it involved in chemical reactions, that's all called thermodynamics. And it's looking at how is energy exchanged, how is it transferred in a reaction. Some reactions you know are spontaneous. So spontaneous means it happens without us having to do anything to it. So if you take an ice cube out of the freezer, set it on the counter, it's going to melt. Okay? So unless it's constantly having heat removed from it, which is the condition when it's in the freezer, it won't stay in its solid form, it'll melt. Iron, if you if nails sit out, if you have metal tools and they sit out, they'll just spontaneously start getting that rusty brownish material around the edges. Wood spontaneously breaks down over time. So it's usually like the bottom of the wood pile, all that wood's kind of like you pick it up and it's sort of starting to fall apart. Those things are all spontaneous. Part of the reason it's spontaneous is it's the nature of the reactants. Iron is reactive. Iron will react with oxygen if it's around, and that causes rusting. Water, as an ice cube, will automatically absorb heat from the room, and it'll allow it to melt. So it allows it to go to a less ordered arrangement. So the nature of the reactants, that comes into play in whether or not it's spontaneous. But now other reactions, they don't happen automatically. So for example, if we build muscle proteins, so building structures typically doesn't happen automatically. Things tend to fall apart pretty easily, but it takes an awful lot of effort to create order, to build structures, making ice. These are not spontaneous, and it's really because the amount of energy that has to go in. You have to put more energy in, and that is why they say that energy that it's referring to, they call it a delta G. That's just like a terminology they use. The energy is positive because we have to put energy in. Whereas if ice melts, the delta G is negative. Negative means I don't have to put anything in. It's actually going to be able to occur spontaneously. So spontaneous reactions don't require energy. Non-spontaneous reactions do. If they release energy, if they have that negative delta G, then they tend to be energy releasing reactions. But if, and in this way, you can think heat is a product in the reaction. So if we burn wood, we form carbon dioxide and water, so we're breaking it down, and it releases enough heat to actually sustain this reaction. As long as the wood is present, it'll continue to burn until it's all gone. But reactions that are endergonic, so endo or ender means to go in, these are reactions that are going to take in energy, require energy. They're going to have, they're not going to be spontaneous. They're going to end up having energy that has to be given or put in. Their delta G's tend to be positive. See, these tend to not be spontaneous. And so in this one, like taking ammonium nitrate, you have to heat ammonium nitrate to get it to dissolve. So it won't dissolve all on its own. You have to add heat to it, or else it'll just stay a solid. This is a cold pack. So if you've ever bought a cold pack that actually has it's a liquid filled material, and inside there's a little bubble, and you have to break it. So you have to break that inner piece. Inside is ammonium nitrate, NH4NO3. And when you smash it and then you shake it, you can hear these crystals. So it's kind of you can hear these crystals rolling around in it. As ammonium nitrate begins to dissolve, it absorbs heat. And so that cold pack begins to lower in temperature. It absorbs heat from the environment, and that's why it feels cold. Those hot packs, the other ones, those, you click this little, it's like a little metal piece that creates a vibration, and it starts a reaction where the opposite occurs. It generates heat as it solidifies, and it becomes warm to the touch. So that you have heat packs and cold packs, and it's really just the different chemicals that they're using in order to achieve that. So you can describe this by using what they call an energy chart. So this is looking at energy and how a reaction proceeds. So if you have, so we'll just say that you have A and B, and you're going to try and combine them so that they'll make C. We're going to take A and B and we want to stick them together so that they're permanently stuck. So in doing that, A and B have a certain amount of energy by their nature. If they have a lot of energy, it doesn't take very much energy in order to get the reaction to occur. So that is called the activation energy. They call it the energy hill. So it's how much energy has to go into the reaction for it to occur. But notice with the second one, A and B are at a lower energy, and it has a much steeper hill, a much higher activation energy that you would have to put in compared to the first one. So do you see how this first one has less energy in and more energy out? So the beginning part of the hill is pretty short, but then it's going to release more energy than it takes for it to go for the reaction to occur. That's why this is exergonic. So exo or exer means to come out. So there will be energy released in this reaction. But over on the other side, notice that it takes more energy than what you get back out. So that is going to require constant input of energy to keep the reaction occurring. So this one requires more energy in, less energy comes out. And that is why they call that one endergonic. Which do you think is more spontaneous? The first one or the second?
First one.
First one, okay? Because it doesn't take as much energy to make it happen, right? So the first part, the hill, is smaller. So this is more spontaneous. More likely to happen because it requires less energy. And you're going to actually get more energy out than you ended up putting in. And that energy can then turn around and run the reaction again, like burning wood. So when you think about activation energy is the amount of energy these molecules need. So if molecules are just sitting there, there's really nothing to get them to combine. So if we wanted to take A and B, we've got to put them together. But if they're just sitting there and they don't have much energy, they're not really moving about. So we want to increase that activity. We want to get them to come together, and they also have to collide with enough energy and in the right orientation. So in this one, you can see they have to have enough energy and collisions. And not only do they have to collide, because like in this one right here, this example, A and B collide, but they don't collide correctly, okay? So we need them to come this way. So if they come up this way, they're just gonna bounce off of each other. Nothing will happen. They have to come together in the right orientation. So molecule shape is really important. We kind of talked about that a little bit when we were talking about chiral molecules and how the shape of a molecule really does affect how it works as a drug or medication. So it has to have collisions and the right orientation. And so in this one, you can see that they come forward, that they're in the right orientation so that they fit together. I always think of like Legos. Like if you put two Legos side by side, they're not going to stay together. You have to stack them. They have to interlock. They have to fit together that way. It's the same thing with chemistry, with molecules. In a reaction, molecules have to fit together in order for that reaction to occur. So how can we change that? So we can change, we're not going to talk about these because we did this in lab, but we can change this rate. We've got to get them to collide. We have to have enough energy and they have to have the right orientation. But there's a couple things we can do that can improve this. So this right here shows this. So in this one, so A plus B makes C. So A is the little red balls, B are the blue ones, and C is them combined. So when you look like in beaker A, can you see all three? So can you see A, the little red ones? You see B, the blue, the medium-sized ones. But C is actually them together. So this is like the typical reaction, A plus B making C. So if we mix them together, we've got to have them moving around. They're going to have to come in contact with each other. They have to come in contact in the right orientation with enough energy in order for the reaction to occur. One way we can speed them up is by doing B. So what is B showing?
Heat.
Yeah. Okay, so what happens when you heat molecules? So remember that temperature is a measure of the vibrational activity of molecules. So if molecules are vibrating really slow, are they moving very fast? No. But if we can heat them up, now they're going to be moving faster, and they're showing this like that they're bouncing off of the walls of the container, and the odds are if they're moving faster, they're going to hit each other more because of that more rapid movement. So by adding heat, that will increase the vibrational activity. That's going to increase collisions. That'll speed it up. So that's the whole premise in cooking. Like this is why you cook food. So food would eventually begin to, would get to a cooked state. It'd probably mold first, but it would get to a cooked state, but adding heat is going to cook it faster. What's the second one? How's the C? Sorry, C. How does C look different than A?
A and B are combined.
But how is, when you look at A and you look at C, what's,
more,
there's more, okay? So that's concentration. If we increase reactants, if we increase the amount of reactants, that's going to increase the odds they're going to hit each other. That's collision. As long as it's in the right orientation, they have enough energy, the reaction will speed up. So increasing reactants will increase collisions. And that can help speed up a reaction. So my example with this is trying to start a charcoal briquette fire. So I'm really not like the barbecuer person. Like, I make all the inside stuff. That's not really my role, my job. If I have to grill, I'm gonna go turn on the gas grill because I got time for all of that other stuff. Because everything will burn inside while I'm trying to play with some fire. But if I'm gonna start a charcoal fire, you go out, you stack them all up, you put some lighter fluid on, and you light them, and you get like a little flame. And then sometimes, you notice like they don't start ashing over really well. Maybe your briquettes are old, maybe they've gotten kind of damp, and so it just doesn't work as well. So how do you speed up that reaction? I just add more lighter fluid. So then you're like, so you soak them down really good, and then you throw the flame, and then the flames shoot up like 10 feet, and you like half melt the vinyl on the side of the house, all of that. But increasing the reactant helps to increase the collisions, making the reaction happen so much faster. So you can add heat, you can increase the reactants. What is D?
Neutral state.
Huh? What is D? What's different about D from A? It has little green things. It has these little cups. These are catalysts. Okay? And the catalyst is doing exactly in that picture really what it does. The catalyst comes along and it actually binds to the reactants and puts them together in the right orientation. So it's not just random. So you're not just waiting for them to go boom, okay? And half the time they bounce off the wrong way. Catalyst will take A and take B and put them together correctly. And that's how it lowers the activation energy and speeds up the chemical reaction. So it puts reactants together in the right orientation, which is half the battle. And that is going to increase the rate of the reaction. This lowers the activation energy. So with heat, we're really just adding more energy to the reactants, and so that's going to help push them over that activation energy hill. With C, we're just putting more and more reactants there so that some of them will go faster over the hill, but catalysts actually lower the hill. So if you're looking at a graph somewhere, darn it, if you're looking at that graph showing the activation energy is actually lowered. So here's an example. So an example is an enzyme called catalase that's in the blood. Catalase breaks down hydrogen peroxide. So if you put catalase just on your skin, if you put peroxide on your skin and it's not cut, nothing happens. It's just clear liquid and it just rolls off. But if there's a cut, then in that fluid is this enzyme. And this enzyme will speed up the breakdown of peroxide into water and oxygen. But in this breakdown, you get the breakdown of tissues within that area. It's an oxidizer. So it is going to give oxygen to other molecules in this reaction. And so that's why you use peroxide to be able to clean a wound. It's really not something that you want to keep using because it fizzes. It doesn't hurt. That's one of the nice things about it. It's not painful, but it fizzes because the enzymes in the blood break down the peroxide, and in doing so actually help to clean that wound. Any microbes in that area end up being affected in this reaction, and they get broken down too. So they'll get oxidized along with the peroxide, and that's how it's used to clean. It's not something that you want to use more than once because it ends up breaking down tissue. And so if you start scarring, if you start having like scabbing taking over and you put more peroxide, it's going to wash all that off. So it's going to actually tear all that down, and you really want all of that collagen formation to occur. But this is how it goes through. In fact, the body has enzymes. Enzymes are organic catalysts that interact with reactants, put them together in the right orientation to lower their activation energy. Enzymes in the body, these can speed up reactions millions of times. Not just like make it happen twice as fast. Like this can cause reactions that would take hours, they can take seconds. So they can really speed up how fast we're able to respond to changes. So my example, what I drew right here, so the little squiggly thing, that's the enzyme. So it looks like a laying down E. And the shape of that enzyme has the ability to bind specific substances. So this enzyme can bind A and B. And so that's in my example. But notice like D and E, the shape of D and E would not fit in this enzyme. So the shape is very specific. The enzyme, when it has the reactants bound, actually changes shape and will push the reactants together. So in that middle one, see how A and B get slid side by side? That's exactly the position they need to be in for a reaction to occur. So you start off, the reactants come in, they get pushed together, the reaction occurs, and so the product, C, gets released. And the thing that's amazing about enzymes, especially the body enzymes, is that once the product is released, the enzyme goes back to its position, and it can do it again, and it can do it again, and again, and again. So enzymes, you don't have to have like one enzyme for one reaction. One enzyme can speed up the same reaction over and over and over again until it wears out. So example, in your mouth, you have saliva. So saliva has an enzyme called amylase. Amylase takes starch and breaks it down into sugars. So it just takes this really large molecule and it begins to cut the connections between the sugars so that they get smaller and smaller and smaller. They have to be small enough to be absorbed. And so that enzyme, one enzyme, can work on multiple starch molecules, just continues breaking it down, breaking it down, breaking it down, until that ends up in your stomach and then stomach acid kills it. But the enzyme works long enough. It's one of the reasons you're supposed to chew your food. You're supposed to chew your food so that all of the enzymes in the saliva can help in this breakdown. In your stomach secretes protein digesting enzymes, and it uses the acid in the stomach to speed the reaction up. So the acids actually promote the breakdown by those enzymes. There's a chart in here that talks about a bunch of them. These are diseases because you're missing an enzyme.
Is this a kid? Like,
It's just some examples. So one of them, albinoism. So albinism is when you're missing an enzyme that is needed to make melanin. And melanin does what for your skin? It gives it a color, right? So it's a genetic disease. You can't make this enzyme, so you can't make melanin. So the skin looks what? White. Okay? If you don't make melanin, there's no pigment in your hair, so your hair is white. There's no pigment in your irises, so your eyes look
Red.
they're pink. They're actually like true albinoism actually will have pink, kind of like a bunny. Have you ever seen like the Snow White bunnies, like the Easter bunnies? They have pink eyes. They're true albinos. So they don't have any of that. But melanin is good because what does melanin do? From sunlight. Melanin blocks ultraviolet light. And so it's actually a beneficial thing. So being super pale is not the best thing in the world because you're more susceptible to sun damage. So they have problems with skin cancer. They have problems with vision because that lack of pigmentation causes more sensitivity. So they have to like go out. So when they go outside, they stay completely covered. They really try to limit any sun exposure because they sunburn so easily. Another one that is a common one, lactose intolerance. So lactose intolerance is not something that you're genetically born with. Some people actually have this as infants. They have to have soy milk because they're allergic to cow's milk or they're allergic to their mother's milk. That is because they're missing this enzyme called lactase. So lactose, which we'll talk about in chapter 6, is actually a disaccharide. It is a molecule of glucose. linked to a molecule of galactose. So it's these two sugars, and they're chemically combined. You can't absorb two sugars together. It's too big. So you make an enzyme that breaks them. So the enzyme splits glucose and galactose. It's secreted by your pancreas. So all this happens in your small intestine. So when you drink milk, it goes through your stomach, not a problem. The lactose keeps going. But once it gets into your small intestine, lactase begins to cut this. So it comes up, snips it in half, and then there are two monosaccharides. Monosaccharides are small enough to get absorbed. So once we break the link, you have glucose and you have galactose, now single, and they get absorbed. Some infants don't make lactase, and then some people, as they get older, they get more and more lactose intolerant. So that means their pancreas stops making this enzyme. So if you don't make this enzyme, then you don't break the lactose into its smaller parts. That means that it doesn't get absorbed. So that means this molecule goes through your small intestine, all 20 feet, keeps going. When it gets down to the end of the small intestine and into the large intestine, you have millions and millions of what that live down there? What inhabits your large intestine? Bacteria, millions of bacteria. You have a whole flora. It's like a whole little community that lives in your large intestine. So if it's not digested, because you're missing this enzyme, bacteria in your large intestine ferment it. They can use it. They like this sugar. It's not a problem. They like sugar. But they're going to then ferment it. When they ferment it, they're going to make carbon dioxide and they're going to make acid. So how does that person start to feel? If your large intestine starts filling up with carbon dioxide, you're like, people say they feel really bloated. They feel like their whole abdomen feels distended. It's because of all of that gas, carbon dioxide, that's actually in the large intestine. The bacteria are making it because you didn't digest that lactose. So it gets digested in the large intestine, but it also makes acids. And acids irritate the large intestine. So cramping becomes a problem. When the large intestine gets irritated, one way to try and flush it is to do just that, is to add water to the large intestine, and you end up with like massive diarrhea. And so that's like, it's really the body's way of just trying to clear it. And so that can be such a bad sensation, diarrhea, bloating, gas, flatulence, nausea, cramping, that can actually be really quite painful, that people just start to avoid lactose altogether. So that means that you don't need any of what? No milk, no cheese, no dairy. You just try to stay away from the dairy. That's like cheesecake. That's like terrible. Okay? So you just stay away from that altogether. No ice cream. All of those.
So when you take lactate pills, does that build those
That's
enzymes?
that enzyme. So they actually sell supplements. You can take pills that are actually just a pill form of this enzyme. So when you eat cheese, you swallow a couple of those pills. They dissolve, and in your small intestine, it breaks down your lactose. That gets absorbed like normal. Another route is that you can also take lactate, like the milk that is lactose free or lactose reduced. All they do with that milk is they treat it with that enzyme. They treat the milk with the enzyme so it's already broken down. So when you're drinking the milk, you're really drinking glucose and galactose. You're drinking it already broken down, and that way it's going to get absorbed easily. So the big challenge is people that are lactose intolerant, if they really avoid all forms of dairy, then they may end up being deficient in what? Calcium. Calcium is really the big issue, because calcium is our main. We're not like big bone eaters, like my dogs. You can give them a bone, they're like, they get a lot of calcium from eating stuff like that, but we really don't gnaw on bones enough. And so that means that we've got to get calcium from other sources. And you can get them from some of the vegetables, but really dairy is the major source where we use calcium to build bone density, to make sure that the bones stay really hard, especially as you get into your 50s and 60s and 70s. And so people that don't end up with running the risk of having osteoporosis, having porous bones because of low calcium. And that can be a reason, because it's really uncomfortable. I mean, it's bad when you're like walking around feeling like someone like pumped a balloon full of air into you. But then also if you have terrible cramps, or if you have really bad gas, or if you have diarrhea, then you're stuck at home kind of thing. So a lot of people will just avoid it. Last one. So albinism increases your risk of cancer. Lactose intolerance is really just uncomfortable, okay? But those are not necessarily life-threatening, but PKU is. So phenylketonuria is when you're missing an enzyme to be able to break down an amino acid called phenylalanine. So it's just a normal amino acid that's present in the diet. So this is genetic, which means that you're born with this condition. To test for this, they do the heel prick on every infant. So if you had a baby, that was one of the tests, is they did a PKU test on your child before you left. Before they did this, they didn't know if a child had PKU. Child would be born fine, have really good scores, go home, be fine, come back at the 6 weeks, was okay, hadn't really put on as much weight as maybe they should have, but then you begin to see by 3 months, by 6 months, you start to see neurological changes. They stop thriving. They stop having normal changes at 3 months, like certain reflexes that you should see. They should be having certain behaviors, holding their head up, looking back and forth. You start to lose those because of damage. So without this enzyme, phenylalanine, this amino acid that's present in protein, is taken in the diet, taken in the milk, but it doesn't break down. And so if it doesn't break down, it begins to build up. And it actually builds up to toxic levels. The kidneys don't flush it, but it ends up causing neurological damage and eventually will cause death. So when they finally figured out that that's all they had to do, if a child has PKU, all you have to do is put them on a diet low in phenylalanine. And there are certain, so they just give them a formula that has very low phenylalanine in the protein. They put them on a diet so that they're always going to avoid meats, certain types of meats that have higher than normal levels of phenylalanine. And then they don't ever develop any of those side effects. So that's one, and understanding that enzyme and what it does allows you to avoid like major issues. All right, so the last thing that I wanted to talk about was just the basic types of reactions to identify. So the one we've been talking about is the A plus B makes C. So that more reactants, fewer products, they always call that synthesis reactions, okay? And it's really easy to recognize. All you see, more reactants, fewer products. So these are the building reactions. So when I think of synthesis, I think of making something. So we're going to take little things, put them together, and make bigger things, okay? More reactants, fewer products. The opposite of that is the decomposition reactions. Decomposition reactions are when you're taking something big and you're going to break it down into lots of little things. Like something decomposes, what does it do? Falls apart, right? When things fall apart, you end up with lots of little things. So in this, you will always have fewer reactants, more products. So notice that those are the opposite. What about reactions where you have equal numbers? If you have equal numbers of reactants and products, those are called displacements. A single displacement is where you have a compound in an element and you have one set of partners that swap. So in this one, A swaps with C. So if you have a compound and an element, makes a new compound with a different element, that's a single displacement. So it's just a single swapping. Double displacement is where you start off with two compounds and you end up with two different compounds. So in this one, the inside and the outside pairs end up combining. So A combines with D, C combines with B. So you have them like this, and they just pair off this way. So that's why they call it double, because it looks like you have two swapped, whereas this one, you just have a single. So in this one, A gets swapped off with C. So you can see these here. So what's the first one? Synthesis, decomposition, single displacement, double displacement. Synthesis. Right, so we have 2 reactants and 1 product. Synthesis. So really easy to identify. What's the second one? It's a double displacement. I started off with 2 compounds, and I have 2 different compounds. So still 2 and 2. So the displacements are going to have the same number. What about the next one? Aluminum carbonate. It's decomposition. Yep, so you start off with aluminum carbonate, breaks down into aluminum oxide and carbon dioxide. Iron oxide plus hydrogen makes iron and water. 2 and 2, so both sides. You have 2 on one side, 2 on the other side. It's a single, single displacement. So see, the hydrogen bumps the iron off, takes its place, iron's all by itself. So when you have an element in a compound making a different element in a compound, that's always a single displacement. What's the next one? Synthesis. Because magnesium and nitrogen combine to make magnesium nitride. Chlorine plus water makes HCl and O2. 2 and 2. So it's a single. Single displacement. I have 2 reactants and 2 products. All I did was I just took the oxygen and swapped the chlorine. So the oxygen ends up all by itself. The chlorine ends up combined with the hydrogen. Next one, synthesis. Calcium oxide plus HCl makes calcium chloride and water. That's a double. So notice I have 2 reactants, 2 products. Both of them are compounds. So they're double swapping, so that's a double displacement. And then the last one, synthesis. So those ones they're like really not that hard. They're just ones, if you have more reactants, synthesis. More products, decomposition. But if they're equal numbers of reactants and products, if one's an element, one's a compound, that's a single. If they're both compounds, then that's a double. Okay? So that's why I was like, if we can get to here, because those are really pretty simple. Like chapter 5 is really not a bad chapter. But we will stop there. And I actually took chapter 5 and split it. So I've split chapter 5 into 5A and 5B. So I took all the stuff that we weren't going to cover, and it's over in B. So that will be on the 3rd exam. So go ahead and do it. I think there's only 10 questions now in chapter 5A. So finish chapter 5A. If you run into any problems with doing the chem draw or any problems in MyLabs Plus, let me know. You know that we do not have class Monday and Tuesday. Everybody knows that? Because it's fall break. Okay, so I won't see, yes, no classes Monday or Tuesday, it's fall break. I will be on campus Monday and Tuesday, so if you do have any questions or anything, do feel free to send me an email, because I've got a whole bunch of grading I have to do. I'm not going anywhere. I'm not very excited about it.